Now, if you had a pure material, you could put it on a probe and insert that probe directly into a mass spectrometer so that it's positioned in front of the electron source. But typically, the samples that we want to look at are not pure materials. And if we put a mixture directly into the mass spectrometer, then we'll end up with a spectrum that represents the mixture, and that would be very difficult to interpret. So what's most common is to use a separation technique as a means of introducing a mixture into the mass spectrometer so that we have pure zones entering the mass spectrometer sequentially, and then we have a pure material. So this schematic is for a gas chromatograph. In the first semester laboratory, you used a GC. You can think of this in its simplest conception as a boiling point separation. You have a heated oven, a sample, and the analytes in the sample must be volatile. That's a requirement for gas chromatography. The sample as a liquid or a solute dissolved in a solvent is injected. This oven can be held at a constant temperature, or the temperature can be programmed to follow a gradient to bring the highest boiling components off more quickly. And as they are eluted from the separation column, there's a transfer line, and these gas phase molecules enter into the very low pressure regime of the mass spectrometer. They're ionized by the electron beam, and then using electric fields and magnetic fields, they can be focused and sorted, and then strike the detector to collect the data. When we do a hyphenated technique like GCMS, we have 2 dimensions of data. We have the chromatogram. So this is the boiling point separation. And these are the zones of pure compound that are being eluted. And then for each peak, we collect a mass spectrum. So that is a third dimension of data. So this is very, very powerful because now you have an array of data that you can use for identification, and with computers, library searching and that high data density can be very useful, and this is commonly used in environmental analysis where no human interpretation of the spectra is going on. It's all computer-based. This is also good for, the Olympics have just started. GC Mass Spec is how the organizations that monitor doping of athletes perform their analyses. Often, if you were in the military and subject to random drug screening, often the first screening test is a low resolution test, inexpensive, because of the large number of samples. And then if there's a positive, those tests are not you wouldn't want to have disciplinary action or criminal penalties based on an enzyme-linked immunoassay. But anything that's positive in the screening test typically gets shunted off for GC Mass Spec confirmation. So I mentioned for GC, the requirement is that the molecules must be volatile. Up until about 30 years ago, it was really impossible to get a mass spectrum of larger molecules, because when you heat them, rather than volatilizing, they decompose. But in the past several decades, electrospray ionization, there are other soft ionization techniques, thermospray, electrospray. There are probe techniques. There's been a real tremendous development of mass spectral ionization techniques, laser desorption. But very commonly now, biomolecules like the GC experiment, but instead of GC, using a liquid chromatograph, a mixture of biomolecules, be it a blood sample, if you're doing monitoring of metabolites in a patient in a clinical trial, um, blood sample typically would undergo some kind of fractionation before it's injected. But the biomolecules will be separated chromatographically and then through electrospray ionization enter into the mass spec, and you can collect a mass spectrum of the individual components of a mixture that way. All right, so the last thing here is degrees of unsaturation and hydrogen deficiency index. For an alkane, the molecular formula is C subscript N, and hydrogen is given as 2N plus 2. So if we have propane, CH3, CH2, CH3, the plus 2 here accounts for the methyl groups, which have 3 hydrogens, and all of the carbons in the chain for the methyl groups are just 2. So this is very useful. Going to this concept, if we have pentane, C5H12, pentene, C5H10, and pentyne, C5H8. These two molecules, we're short 2 hydrogens here, and we're short 4 hydrogen here. So this is 1 degree of unsaturation, and this is 2 degrees of unsaturation, because every degree of unsaturation results in the removal of 2 protons. So if we look at the formula C4H6, well, for a saturated hydrocarbon, we would have C4, and H would be 2 times 4 plus 2, or H10. We have H6, so there are 4 hydrogens missing, and our degree of unsaturation is 2. There are a number of ways you can have 2 degrees of unsaturation. You could have 2 double bonds, 1 triple bond, 2 rings, 1 ring, and a double bond. Now this is important because calculating the hydrogen deficiency index, if you have no degrees of unsaturation, you know immediately that you have no rings and no double bonds. And depending on if you do have a value for deficiency index, then it can help you look for the important functional groups that would account for that, the double bonds, triple bonds, and ring systems. Now, when you're looking at something more complicated than just a hydrocarbon, you need to think about what is the impact of the other atoms. So in the case of a halogen, you would treat this as if it were a hydrogen atom. If you have an oxygen, it doesn't affect the calculation of the hydrogen deficiency index, but nitrogen does, because there will be a 1 fewer hydrogens from the presence of a nitrogen atom. So there's you can remember these, or you can use the hydrogen deficiency index equation shown here. And then, as I mentioned, this can be useful because if you have a hydrogen deficiency index of 0, you know that you're not looking at any rings, double or triple bonds. So that closes out our mass spectroscopy unit.